Hi, everybody. My name is David Tear. Welcome back to Dave's Math Channel. Today I'm going to talk about the golden ratio. This is a very important number in mathematics. It's equal to the square root of 5 minus 1 over 2, and it's approximately 1.618. This is considered one of the most important mathematical constants there is, nearly as important as pi and e square root of 2 and stuff like that. Anyway, the reason it's so important is because it's probably the most aesthetically pleasing ratio there is. And here in this picture I show what's called the golden spiral, and this is built on what's called the golden rectangle. So if you look at this spiral, it's constructed by these rectangles here, and look at the whole big rectangle to start with, all the way up to this line on the right, and then the borders of the picture. It turns out that the ratio of the length to the height of this rectangle is the golden ratio, about 1.618. And one nice feature of the golden ratio is that it's equal to itself plus its reciprocal. So what that means, if you have a golden rectangle, you can you can partition it to a square, and you can see the part on the left is a square, and then the part that's remaining is another golden rectangle, except this one turns sideways. If you look at the portion on the right, this is another golden rectangle, and then you can keep dividing it the same way. So now this golden rectangle on the right has a square in the upper right, and another golden rectangle like the one we started with, this one going horizontally again, and you can keep doing this ad infinitum. And when you're done with this construction, this is just, I think, 10 stages of the construction. You could do it as many times as you want. But if you look at the spiral, the way you make a spiral out of this is if you look at the left, you have an arc of a circle. This is a quarter circle going upwards for the bottom left corner of the golden rectangle up to the top right of the square on the left, and then you make another arc, a smaller arc, going from the top left the top left of the square on the right, on the upper right, and you go down to the bottom right corner, and then you keep going like that. You keep drawing more and more circular arcs, and when you do that enough times, you end up with a spiral, a beautiful spiral, and that's known as the golden spiral. And another way you can construct an approximation of the golden spiral is you can use Fibonacci numbers. So it turns out that the ratio, there's a very deep connection between Fibonacci numbers and the golden ratio. These numbers on these squares, by the way, are all Fibonacci numbers. We're starting with 1. 1 is the first Fibonacci number. That corresponds to this little white square in the middle, sort of the lower right part, but the middle of the diagram where the spiral starts. And then there's another 1 by 1 rectangle right next to it. So 1, 1, that's the first two Fibonacci numbers. The second one's 2, which is 1 plus 1. So now you got a 2 by 2 purple rectangle above that, and then you got a 3 by 3 blue, kind of a indigo or blue violet rectangle to the left of that, and then you got this one with a number 5 in it. That's a light green or light blue square. You keep going like that. Each of these are squares where the sides are Fibonacci numbers, and since the ratios of neighboring Fibonacci numbers approaches the golden ratio, this spiral, it's called the Fibonacci spiral. It's not exactly the same as the golden spiral, which I showed earlier, but it's a very good approximation. So that's a good way to construct the Fibonacci spiral. And the Fibonacci spiral, golden spiral, are examples of what's called a logarithmic spiral. And notice this is a chamber nautilus. This is, I guess, a cross section. Somebody cut it in the middle. But the chamber nautilus is a pretty remarkable animal. It's like a kind of a snail. It lives in the underwater. But notice these are chambers that it grows out of as it grows. And notice how it grows. I mean, this is a naturally occurring animal. This is a naturally occurring shell. The chamber nautilus, which is like a little snail inside, keeps adding more and more to its shell as it grows. Finally, this is where it finally stopped growing, and notice the shape. It's a logarithmic spiral, and that's just a fact of nature. And So logarithmic spirals are very important. They occur a lot in nature. Snails and nautiluses have this shape, and it's very close to a golden spiral, which I showed you earlier. So these things occur in nature a lot, and there's other applications. It turns out flowers obey the number of petals on flowers as Fibonacci numbers. That could be a whole number video. I'm not going to talk about that here, but anyway, that's the Fibonacci numbers in nature. And one more mathematical fact I want to say about the golden ratio. This diagram here is what's known as a pentagram, or more simply, a five-pointed star. I'm sure you guys are all familiar with those. There's 50 of them on our American flag. But one pretty amazing feature of the pentagram, look at these different line segments it's composed of. So the longest line segment in the pentagram are these black ones. And then the second longest is the green one. And if you take the ratio of the length of the black segment to the length of the green, or no, I'm sorry, the red, no, the red is the same as the black. The green is the second longest. So the ratio of the length of the red to the length of the green turns out to be the golden ratio again. And you can do it two more times. The ratio of the length of the green, the third longest segment is the blue. So the ratio of the green to the blue is also the golden ratio. And finally, the ratio of the blue to the violet. The violet's the shortest segment. That's also golden ratio. Pretty remarkable. So there's a very strong connection between the golden ratio and the pentagram, or the five-pointed star. That has some important mathematical consequences. Let's look at some more how the golden ratio appears in art. So Leonardo da Vinci, who's considered one of the greatest artists of all time, he was also a mathematician, and he used a lot of math in his art. For one thing, he used perspective. He was one of the first Renaissance artists to use perspective, which is a mathematical property of things getting smaller that are more distant. He knew the mathematics of perspective, but not only that, he knew the mathematics of the golden ratio, and he used it extensively in his art, in particular the Mona Lisa, which most people consider one of the greatest works of art of all time. Notice that here's a golden rectangle that fits very neatly into the Mona Lisa and all her proportions. I guess if you go from the bottom of the picture to the bottom of her chin, that's a square, and then you have a golden rectangle remaining, and the height of that second golden rectangle is the height of her head, from her chin to the top of her head, and then you can keep going. And notice her face is confined to the third golden rectangle, and then I guess you can do the rest yourself. But anyway, he did make very very detailed use of the golden ratio in the Mona Lisa, and also his second most famous painting, The Last Supper. Notice these are golden rectangles and squares, and the ratios of these lengths are the golden ratios. So you can see how it fits into this picture very nicely. And not only art, but architecture as well. It turns out the Parthenon, which was an ancient Greek, very famous ancient Greek temple, that if you look at the front of the Parthenon, you see the golden rectangle on that as well. So I guess the ancient Greeks also knew about the golden ratio and used it pretty extensively. And not just Western architecture, but the Taj Mahal in India. Notice the front of the Taj Mahal, how the golden ratio, golden rectangles fit in with that as well. And modern architecture too, the United Nations. I think this was built in 1945. This is the UN headquarters in New York City. And notice that the side of the UN is divided into three golden rectangles. That's how it was designed. One last thing I'm going to mention, the pyramid, the Great Pyramid of Giza, also involves a golden ratio, but not in quite as simple a way as the other ones. And the Great Pyramid is pretty amazing in its mathematical properties. If you call the sort of radius of the base 1, or the side of the base 2, and then you look at the lengths of say the altitude of one of its triangular faces, that altitude is equal to phi, which is the symbol for the golden ratio, which I said earlier is about 1.618. And you get it twice. Actually, you get the square root of phi too. If you look at the height of the pyramid, the height turns out to be about the square root of phi. And there's one more numerical coincidence I just want to mention very briefly. It turns out pi also appears in the geometry of the Great Pyramid. It turns out that if you take the ratio of I believe it's the circumference or the perimeter, which is 8, and then you divide that by the height, or yeah, something like that. Maybe 8 divided by square root of phi, that's too big. I think that's 2 pi. Yeah, so that's kind of a numerical coincidence. It turns out that 8 over the square root of phi is very close to 2 pi, or 4 over square root of phi is very close to pi. It's not exactly pi, but it's very close. I think within a few parts in 1,000. So anyway, that's my talk on the golden ratio. I hope you enjoyed it, and I'll see you next time. Bye.